Good afternoon, everyone. Welcome to the fifth lecture in a series of lectures on field and Galois theory. Today, Adrita will start with fundamental theorem of algebra proof and then revisit proof theory. Adrita, please start.
Yeah, so hello everyone. Today first we'll see an application of Galva theory to prove the fundamental theorem of algebra. So the fundamental theorem of algebra, or FTA for short, it says that any polynomial P in C of X has at least one root in C. Now this is also stated as the polynomial has all roots in C. So if the degree of the polynomial is n, then the polynomial P has n roots in C. But if it has one root, a simple induction shows that it has all the roots because C is a field. Similarly, we can also state this as C is algebraically closed. So these are equivalent statements. Now the first proof was given by Gauss and simultaneously a little while later by Argan. And since then, they have come up with a lot of proofs of this theorem. So there is a topological proof which uses the concept of winding number. There is a complex analytic proof which uses basic complex analysis and Liouville's theorem to prove the existence of truths. Then there is a proof using simple real analysis in two variables and inverse function theorem and some concepts of topology to give the proof. So what today we are going to do is give an algebraic proof. Now, the problem with giving a completely algebraic proof of FTA is the fact that C cannot be constructed without some basic topological or analytic facts. Any construction of C requires some background in real numbers or some sort of concept of extension of the real numbers. Now, the real numbers have been constructed in a lot of ways, and all of them are analytic. For example, there is one with the one by Dedekind, then there is by the closure, and all of these require some analytic ideas. So this theorem cannot be proved completely algebraically. But using Galva theory, we can keep the algebra, the analytic factor, to a minimum. So we will make a few assumptions, and that will be all for our analysis part. So we give the proof. First, we say that so our first point is R over C is a finite field extension, and they are fields of characteristic 0. Secondly, any polynomial P in R of X of odd degree has a root in R. Now, this has a very simple proof using intermediate value theorem for continuous functions. So, any polynomial, if we take an odd degree polynomial, we can make it a monic polynomial because R is a field. And then as x tends to minus infinity, the polynomial is negative. And as x tends to positive infinity, the polynomial takes positive values. So by the intermediate value theorem, it must take some value. There must be some value in between such that the polynomial is 0. Now this property inherently uses the completeness of R. So for example, if we take the polynomial over Q, it need not be that the polynomial takes real roots. So for example, over Q, if we consider the polynomial, so say x minus root 2 times x plus root 2 times say x plus root 3, this polynomial does not take roots in Q. So this is a property of R. Now, so this is our second assumption, and our third assumption is the following. So what we have is that C has no extensions of degree 2. Now, what does this mean? This means that every element, so this is equivalent to saying that every element of C has a square root. And this we have already seen that this is an easy verification that every number has a square root. So this is a simple algebraic calculation that we can verify. Now, these both are the facts that we'll be using from analysis. And what we will do is we will be translating these analytic facts to group theoretic facts using Galva theory, and then we will use simple group theory to prove the fundamental theorem. So what we do is first we assume the following. So we have R and C. So this is a degree 2 extension, and then we have Cx. So where x is a finite normal extension of R containing C. Now, why do we assume such a thing? So suppose C is not algebraically closed, then there exists a polynomial over R such that the polynomial does not have all roots in C. So when we attach those extra roots to C, we get an extra extension. So we get a higher extension, which is what we call X here. So we assume that there exists such an extension. And what we want to show, so it is enough to show that X is equal to C. Now we will translate this fact to a group theoretic fact. So first observe that X over R is separable because the extension is finite extension, and the real numbers have characteristic 0. So this implies that X over R is a separable extension and it is normal by assumption. So we assume that X is our normal extension. Now we can say that this is a Galois extension, so we can take the Galois group. So let G be the Galois group of X over R. And by the fundamental theorem of Galva theory, we know that subgroups of G have a correspondence with the extensions R, L, and X. So this is given by the fundamental theorem, and we'll use this to translate the previous facts to into the group theoretic language. So the first fact that we have is that we know that we already said that the polynomial of odd degree has at least one root in R. So the fact number 2 that we stated above, that implies that there does not exist extensions of R of odd degree, except of course the trivial one. Now, using this, what we can say is the following. So we have X over R, this is equal to mod G. Now this was another equivalent definition for an extension to be Galois, that is the degree of the extension is equal to the order of the field, the order of the group generated by the extension. Now we can break it down. So since L lies between X and R, we can say that the degree of L over R is equal to, the other way around. The degree of X over L, this is equal to mod H, where H is the Galois group of X over L. Now what we do, we use the tower property for field extensions. So we have X over L times L over R. This is equal to mod h times the index of h in G. So this is Lagrange. So this, we already know that this is the LHS is equal to x over r, and we use the tau property to break that down. And this is equal to mod G. So this breaking down is due to Lagrange's theorem. And using this, we can see that this and this are equal by the fundamental theorem. So the extension, the degree of the extension L x over L is equal to mod h. So we see that, so this is the real numbers are. So this is equal to the index of h in G. So from here we can conclude. So from here we can conclude that any subgroup of G of odd index is G. So it's not note that it is not the order of the group, but the degree of the order of the subgroup, or the degree of the subgroup that we are considering here. So moving on, this was the first. This was the translation of the first fact to the group to the theoretic fact, and secondly, we suppose that H is the subgroup that corresponds to C. So what we are saying is H is equal to the Galva group of X over C. So by 3, so what did 3 say? 3 said that C has no extensions of degree 2. So using that fact, we show that H has no subgroups of index 2. So similar to the above proof, what we can do is that we take the extension, and then if we have a subgroup with index 2, that will imply that C has an extension of degree 2, which is not possible. So we have that the group H has no subgroups of index 2. So what we have here is we have two facts. So the first fact is G has no subgroups of odd index, and secondly, H has no subgroups of index 2. Using this fact, so using these translations, what we have is G is a subgroup of, H is a subgroup of G. So it is enough to show that H is equal to identity. So what we are showing that what is H? So H is the Galois group of X over C. If it is identity, that means X is equal to C, or rather X is isomorphic to C. And hence we have shown that any extension X that is over reals and is normal is actually equal to C. So what is the next? Now we are done with the proof. We are almost done with the proof. So we pick a silo, pick a silo 2 subgroup of G. Now this has odd index because we have already seen that it cannot have an index of a group of index 2. So this has odd index. Okay, so this is because of the property of the Silo group. So the Silo group is the group which has the highest power of, so the Silo 2 subgroup has the highest power of 2, because any Silo P subgroup has the highest power of 3, and hence whatever is left has an odd index. So the conjugacy classes are odd, and by 1, so since this has odd index, so by the property 1, this implies that it is G. So we from this we can conclude that G is the order of G is 2 to the power n for some natural number n. So where n is greater than equal to 0. And this implies that all subgroups of G are of the form 2 to the power n. So therefore, we can conclude that mod H is 2 to the power m for some m. But we already know that H has no subgroups of index 2. So if m is greater than or equal to 1, we have the identity as a subgroup of, the trivial group as a subgroup of H, which has an index of power 2. Or if we have m greater than equal to 2, we get one less subgroup which has index 2 and which is a contradiction. So this implies that m is 0 and therefore H is equal to identity, and our proof is done. So this gives us a algebraic proof for the fundamental theorem of algebra. Now we will move on to show what we started with during this series. So what we wanted was to show that whether a polynomial f has a simple root, if its roots can be expressed as a radical. So we already have Sridharacharya's formula, which says that degree 2 polynomial can be expressed as a root. So we already know that we can write it as minus b plus minus root over b square minus 4ac by 2a. So any polynomial of degree 2 can be written in terms of radicals. So what does it mean? It means that we can write the roots in terms of the simple arithmetic operations, plus, minus, multiplication, division, and taking nth roots. So the question was whether we can do it for higher degree polynomials. And as a matter of fact, we can do it for cubics and quartics, but it turns out that we couldn't do it for quintics. And our next code will be showing all these facts. So before going with that, we use polynomials to generate Galois groups. So first, we will look at Galois groups of polynomials. So what are these? So we take a polynomial f in fx, and f is separable. Then we take the splitting field. So say f is the splitting field of f, and the splitting field is Galois over f. So ff over f is Galois. Because it's a splitting field, it is Galois, and hence we can just define. So say we call gf to be the Galois group of ff over f, and this gf is the Galois group of f. Now using this, we will show some facts, but before proceeding, we look at this Galois group and see some of its properties. So we know that the Galois group consists of groups, so it's a subgroup of the group of automorphisms, and it fixes f. So we can say Galois gf over f. So this maps roots of f to roots of f. So if f has roots, say alpha 1 up to alpha n, so this is mapped to alpha 1 up to alpha n. So obviously it's a permutation, and we know that since gf, this is a subgroup of odd f, therefore this action is a permutation. Next, we note that so ff is actually generated by f attaching these roots alpha 1 up to alpha n. And what we do is we take sigma, which is in the Galva group, which is in GF, and sigma is uniquely determined. So how is it uniquely determined? It is uniquely determined by the permutation which takes the roots, and given this permutation we can get sigma, and similarly given sigma we can get this permutation. So there is a 1-1 correspondence, and hence it is uniquely determined. So we can conclude that GF, this is isomorphic to some group H, which is a subgroup of the group of symmetries of these alpha 1 up to alpha n, and this is isomorphic to the group of symmetries Sn. And from here we can conclude the following. So we know that ff over f, this is equal to the order of GF. So this is by again the definition of Galva extensions. And since GF is a subgroup of Sn, we can conclude that ff over f, this divides n factorial. So this is another fact of why the extension should divide the degree of the factorial of the degree of the polynomial. So from here what we can say that in general, if we can write f of x equal to f1x up to fkx, such that degree of fi is ni and for I equal to 1 to k, then since GF permutes the roots of the irreducible factors among themselves, we can say that the Galois group of this polynomial ff over f is actually a subgroup of Sn1 times Sn2 up to Snk. So these are all direct products, and so in general this is a subgroup of S summation ni, but we can actually give it a better tell it as a better subgroup. So from here we see some properties of the Galois groups of polynomials. Now we move on to what we wanted to do, the algebraic extension, algebraic equations. So our next topic is solvability of algebraic equations. Okay, so first we take a polynomial. So say f is in f of x, and we want to show that we want to express the roots as radicals. So question is, so what is our goal? Our goal is to find if fx equal to 0 is solvable by radicals. So what does it mean? As I already said, that it is solvable by radicals if it can be, if the roots, so this is equivalent to saying the roots can be obtained by the algebraic operations, addition, subtraction, multiplication, division, and taking nth roots. And this is what we mean by solvability by radical. And our question is, for example, so if we can write degree 2, so up to what degree can we write the radical expansion for different polynomials? So we give a definition. We write this in a more sophisticated manner. So our definition is f is solvable by radicals if there exists a chain of fields. So we call f equal to f naught over f1 up to Fm such that two properties. First, we have Fi equal to Fi minus 1, alpha I to the power mi, where alpha I to the power mi is in, sorry, Fi alpha I, where alpha I to the power mi is in Fi minus 1. And second, so we are taking the nth roots, and the other four operations are already included by the properties of the field. And secondly, we have that field extension is a subgroup of the final field Fm. And this is actually solved by a very fundamental theorem, which we shall see in our next talk. So the theorem that we will eventually prove is the following. So let F be a field where it has characteristic 0. We take F in f of x, then f of x equal to 0 is solvable by radicals if and only if GF is solvable. Now note that we say that the group GF is solvable, and our next code is to look at what this means. So we will now look at solvability of groups. So our next topic is solvable groups. All right. So first we give a definition. What are solvable groups? So the group G is solvable if there exists a chain of subgroups of the form 1, which is 1 equal to G naught, which is in G1, G2, up to say GS, which is equal to G, such that Gi plus 1 over Gi is abelian for all I equal to 0 to S minus 1. So this is called the solvability of groups. And we, before proceeding, we give another definition. So this is something we have already done. So in our group theory course. So what we have, a group G where mod G equal to N is simple if mod G equal greater than 1. So it's a non-trivial group, and the only normal subgroups of G are 1 and G. So these are simple groups, and as you already know that En, so the group of even permutations, so the group generated by the group generated by 3 cycles, or the group of even permutations, so that is simple. Now what we can now we look at solvability. So obviously every abelian group is solvable, and as another example, the group D2n, so the dihedral group of order n, is solvable for all n greater than equal to 1. So we'll not give a proof, we just leave it as an example. And what we want to show is the following. Sn is not solvable. Now, why are we interested in Sn? So recall that in our previous lecture, we had shown that we can write any group as a Galois group of some field extension. So in general, we can write Sn as the Galois group of any field extension. And what using the previous theorem that we stated, we can say that if we get So if we get a group which is not solvable, we can say that the polynomial which generates that Galois group is not solvable by radicals. So it boils down to finding a polynomial which gives the Galois, which has the Galois group S. So we will look at that later. So first we want to show, and since there exists such polynomials, all we want to show is that Sn is not solvable. Is Sn is not solvable. So we will give a proof of the insolubility of Sn. So it goes as follows. What we have first is that An.
Have you assumed n greater than equal to 5?
Yes, sir. Sorry, I missed that. We will have n greater than equal to 5, and we'll also show that, sorry, for n greater than equal to 5. And we'll also show that the other subgroups, so the other groups for S1 up to S4, they are solvable, and hence we have radical expansions for polynomials up to degree 4. So first we observe that An is normal in Sn, and we already know that. So this is our first fact. And secondly, we know that N is simple for all n not equal to 4. So we use these two facts. So why A4 is not simple? A4 is not simple because we have the client group sitting in A4, which is normal in A4. Okay. So what we want to prove is that there does not exist a normal subgroup of Sn other than A. So this is something. So this is what we shall show. So before proceeding, we give another small definition. So it says that we have a group G, and we define its commutator subgroup G prime is defined to be the group generated by all elements xy times x inverse y inverse, such that x and y are in G. So what we are defining is a abelian subgroup of G, and it is easy to see that any conjugate of the commutator is also a commutator, and from this we can conclude that G prime is normal. So G prime is normal in G. This is because the conjugate of G prime is equal to G prime for any element. And we give these two propositions. So first, G prime is trivial if and only if G is abelian. So what is the reason behind this? So if G prime is trivial, we see that xy times x inverse y inverse has to be trivial for all xy, and this implies that xy inverse is x inverse y inverse, which implies that all elements commute, and hence G is abelian. And similarly, if G is abelian, then the commutator subgroup is trivial. And the second proposition that we give here is G over G prime. So this is the group. Because G prime is normal, we can define the quotient group. So this is the largest quotient of G. Now, why is this? So we give the proof here. So take any subgroup. So for any H normal in G, we have G mod H is abelian. if and only if G prime is a subgroup of H. So how can we say this? We can say this since x comma y times H, this is equal to xh times yh. So what is x comma y? X comma y is xy, x inverse y inverse. So this is called a commutator, and these are the elements of the commutator subgroup. And from this we can conclude that G quotiented by G prime is the largest quotient because it is contained in any normal subgroup of G. Now we give the following theorem. So our first theorem is for all n greater than equal to 2, Sn prime is equal to An. Now we note that Sn over An, this is isomorphic to plus minus 1, and this is abelian. And next we have that Sn prime is a subgroup of An because this is abelian, and we have already shown that this is the largest quotient possible is by Sn. So so any normal subgroup contains the group S. So any normal subgroup contains the group Sn prime. And next we have Sn prime is non-trivial for n greater than equal to 3. So why is this? This is because of the easy fact that S3 and above are not abelian, and Sn prime is normal in Sn, and An is simple. And from this we can conclude that Sn prime is equal to An, since it's normal and An is normal. So An contains Sn prime, and again An is contained by Sn prime, so they have to be equal. Now we are left with the case n equal to 2. So for n equal to 2, we can verify by hand. So what we have S2 is 1 comma 2 and 2 comma 1, and this is generated by these two. So this is generated by a single 1 comma 2, and the subgroup that we have A2, so this is equal to identity, and since S2 is abelian, it also has the identity element itself. So S2 prime is identity because S2 is abelian, and hence A2 is equal to S2. Sorry, S2 prime. Okay, and now we give the next theorem. This is the final theorem before proving the insolubility. So this is as follows. So An prime is trivial for n less than equal to 3. Second, A4 over A4 prime, the index is 3. And thirdly, we have An prime is equal to An for all n greater than equal to 5. So this shows that there is no other normal subgroup. We'll come to that later. So first, let us prove this theorem. So the proof of 1 is easy. So we already showed that 2 is trivial because it's identity. Now for 3, it is trivial because we have A3. This is equal to, so this is generated by the element 1, 2, and 3. So again, A3 is abelian, and hence the commutator group is trivial. So this gives 1. Then for 2, A4 has the Klein 4 subgroup. So say K is the Klein 4 group, and we know that K is contained in A4 and it is normal. So what we have, K is isomorphic to Z2 cross Z2, and K has no normal subgroups. So this is a normal subgroup, and this is of order 4. and A4, this is of order 12, and hence K is equal to An prime, and from here we get that A4 over A4 prime, this is equal to 12 by 4, which is 3, and that was our second claim. Now the third claim is again by simplicity. So An is simple for all n greater than equal to 5, and this implies that An prime is equal to An, because An prime is normal in An, and this is the theorem. Okay, now we come back to solvability. So we have already seen that A2, sorry, S2 and S3, these are solvable. Now for S4, we have identity, the client group A4 and S4. So this is a solvable series, because at each point we have normality, and at each point the quotient gives us an abelian group, and the abelianness of A4 by K is since the order is 3, then hence we can conclude that it's a cyclic group of order 3, so it's isomorphic to Z3, and hence it is abelian. Now a very deep result, so we can extend it from the odd order. So a deep result called Feet function. So this states that every group of odd order is solvable. And we cannot prove this at this moment. This requires a lot more development, and we shall not go there. But this gives us that every group of odd order is solvable, and from that we can see that A4 is solvable, and hence S4 is solvable. Now we finally come back to the theorem that we wanted to prove, which says that for n greater than equal to 5, Sn and An both are not solvable. Okay. So this proof is again using the previous two theorems. So what we have is Sn prime is equal to An, and An prime is equal to An for all n greater than equal to 5. Therefore, any chain that we have is of the form identity An and S. And we can have as many Ans and Sns in between, but in general, there cannot be any other group involved in this chain. And we see that this quotient, so we can quotient An by 1, is equal to An, and this is not abelian. So how do we conclude this? So first we observe that A K is a subgroup of A n for all k less than equal to n. So this subgroup is not a normal subgroup, because we already saw it doesn't have any normal subgroups. But all AKs are contained in An for any k less than equal to n. And in general, in particular, A4 is contained in An. And we know A4 is not abelian. So we know A4 is not abelian. We can do the following. We have 1, 2, 3 times 2, 3, 4. This can be broken down into 1, 2, 3, 4, and then we have 2, 3, 4 times 4. This is 1, 3 and 2, 4, and these are not equal. So A4 is not abelian, hence An is not abelian, and from that we can conclude that Sn is not solvable, and hence An is also not solvable for any n greater than equal to 5. So we have the insolubility of N and S. And from here, if we get a polynomial And using the previous theorem that we stated, we can say that the Galois group, the polynomial is not solvable by radical. So our goal is now to show that there exists a polynomial f such that gf is equal to Sn. So before giving this, we give two definitions. So first, we have so say x1 up to xn. These are some indeterminates. And then we define elementary, symmetric functions. So what are they? So they are S1 up to Sn, defined as follows. So S1 is x1 plus up to xn. S2 is x1, x2 up to xn minus 1 xn. So all two permutations. And finally, Sn is the product, x1 up to xn. Now these are all elementary symmetric polynomials. And second definition is we define the general polynomial of degree n. We denote it by Fn. Fn of x is x minus x1 up to x minus xn. So this is a polynomial of degree n with the roots x1 up to x. Now clearly we can see that we can write the general polynomial in terms of the symmetric functions. So using Vieta's formula, we can say that Fn, which is equal Fn of x, is equal to x minus x1 up to x minus xn. This is equal to x to the power n minus s1 times x to the n minus 1 plus s2 x to the n minus 2 up to minus 1 to the power n s. So this is a simple application of Vieta's formula. And finally, we shall show that this polynomial, the general polynomial Fn, generates, this general polynomial gives us the Galois group as Sn. So we define a few more things. So let F be a field. Then we can define two different extensions. So we have f of x1 up to xn. This is an extension attaching f with the indeterminants x1 up to xn. And we can define f of s1 up to sn. So from here we can see that this is a Galois extension of this. And hence we can, so why can we say this? We can say this because the previous field f of x1 up to xn is the splitting field of the general polynomial, and the general polynomial is a polynomial in the lower field f of s1 up to sn. And from here, okay, so before giving the theorem, we define another thing. So we take any sigma in Sn, then, and we take a polynomial f in f of x1 to xn, and we can say sigma acts on f. So f of x1 up to xn. So we can make sigma act on f to give f of x sigma 1 up to x sigma n. So the permutation commutes the elements with respect to the indices. And this gives us Sn is a subgroup of the automorphism group of x1 up to xn. Okay, so all we have to show is the group of automorphisms is exactly equal to S. Okay, so the theorem that we have here first is that fixed field of Sn acting on f of x1 up to xn is f of s1 to s. Now this is quite easy to see. So from the above definitions, we can see that f of S1 up to Sn, this is contained in the fixed field. So call that f of f, f subscript f. So it's already contained in the fixed field because no matter how we permute, because they are symmetric polynomials, the polynomial remains the same. So this is contained in the fixed field. And next we give the final proof using the degree. So by the fundamental theorem of Galva theory, since the extension is Galva, we get f of x1 up to xn. This over f of f is equal to mod of Sn, which is n factorial. And also we have f of x1 up to xn over f of s1 up to Sn. This is less than equal to n factorial. Why? Because this is the splitting field of a degree n polynomial, and hence it must be less than equal to n factorial since it divides n factorial. And from this, these two so this inequality and this equality, we can conclude that f of f is equal to f of s1 up to Sn. Now, why can we conclude this? We can conclude this because f of s1 up to Sn is a smaller field than f of f by the previous inclusion. And since it's a smaller field, the degree must be larger, but we cannot go any larger than n factorial. So what we must have is an equality. Okay, so we have this, and then so from this we can define ff to be the field of symmetric function. Now we give the following corollary, which is quite simple. So any symmetric function in f of x1 up to xn is a rational function of s1 to s. Now, since it's contained in the fixed field, it is a function of s1 up to sn, and since it is a field, the function is a rational function. And this is called the fundamental theorem of symmetric function. And from here we can conclude that the general polynomial Fn has Galois extension. And if we assume the theorem that I stated before, that a group is a polynomial is solvable by radicals if and only if its Galois extension is solvable. So if we assume that theorem, we can see from here that we have polynomials which have Galois extensions Sn, and since Sn is not solvable, Fn is also not solvable by radicals. And that concludes my talk today. So are there any questions?
Sorry, can you recall me what was Fn?
So Fn was the general polynomial. So it was the polynomial defined by taking the indeterminants as the roots. So
This one.
Yes.
Okay.
I don't think there are any other questions. Thank you, Adrita, for the talk. Join us again on 10th of July for the next lecture, where we will discuss the solvability of polynomials by radicals. Thank you.